Hello, am I audible? Please just confirm once, then we can start. So, so till the last class, uh, we have discussed about uh, the monitoring part, the smart grid monitoring part. Uh, yes, it was mostly towards the. Okay, let me check once. Recording is on. Yes, but uh, mostly it was being dealt with. Yes, fine. So, till the last class, we have discussed about mainly the parts that were part of the smart grids that mostly covered the monitoring section, means the wide area monitoring systems, how the wide area monitoring systems evolved, and with the development of the metering facilities, phasor estimation, and everything. Means, but they were mostly related to the monitoring section, how the smart grids evolved, and also there were some parts where which we have discussed regarding the storage systems, because storage systems play a very important role. So storage systems do play a very important role, and okay, let me. And here today we would be mostly discussing about the parts like the protection, how the smart grids, or rather we can say microgrid, how the protection systems develop, and with the increase in the number of metering or measuring devices, how the things have changed rapidly. So we'll wait just 1 or 2 minutes, then we can start. Okay. So till then, for the last class, if you have any questions, you can ask, and thereon we will start discussing about the scenario where the protection or protective equipments, like majorly the monitoring section or monitoring devices, play a very important role that we came to know, and with our aim to minimize the protective equipments, or the equipments rather, not to say protective equipments, to minimize the utility of various uh, means repeated tripping or something like that. So we will have to prevent them from uh, a better way of operation. So to find out a proper and better way of operation, for that we need to develop our the protection algorithms, or the uh, also it is called relay coordination program. So these things needs to be properly developed. So as a part of smart grid, monitoring and equipment protective actions also play a part. And since it's a development of smart grids, so smart grids do take part about the monitoring, but also the other things like protection needs to be taken care of. So let's start this week's discussion, where mostly the initial part will be covered for how the microgrids have been set up and what's the need of microgrids. So here we can see that, so here we can see that mostly our main aim is to, like initial in previously, our transmission systems were the only part who acted as a medium. These transmission systems acted as a medium between the generation and the distribution, that is the generation and distribution. Now in between is the transmission, and the most important thing is that in the transmission part, what we have, this generation and all these things were mostly located in the outskirts, where the raw materials like the coal is, the availability of coal is higher. So this generation part is present far away from the, far away, okay, yes, generation part is located far away from the customer side. And distribution, this is the standard load centers. So where the entire generation that is being done needs to be dumped, or needs to be delivered, not dumped, rather it would say delivered. So for that, our major aim is to have a in between transmission line who used to carry the uh, entire power, means that is being generated, to the distribution side, and then it gets distributed in the load centers. But with the, this is the conventional technique, that conventional conventional mode of power transmission, power generation, transmission, power distribution, etc. And this was unidirectional unidirectional. But now with the previous classes also we have discussed that this smart grid evolution of the smart grids that led to the development of uh, bidirectional power flow with the customers acting as the producers also, because the rooftop solar power plants and all these things are present in the load side. Okay, so with the advent of the smart modern smart grids where the communication interfaces are delivering, means already we had the power network, right? So on the top of the power network we had to implement, or we had to just replace the previous communication technologies with advanced communication technologies, right? So these advanced communication technologies involved communication with various kinds of devices like the metering equipments nowadays, like the smart meters, RTUs, remote terminal units, the PMUs, phasor measurement units. So all these things with faster rate of data transmission, like the DFRs, digital fault recorders. So all these things are being nowadays developed nowadays. So that developed the modern grid communication, and that led to the formation of smarter grids. Now here this conventional bidirectional, which was a unidirectional power flow, which was previously present, that has been replaced with the generation in the distribution side. Okay, and the generation, here we have the load centers, and since the customers are previously it was mostly the utility centric, means whatever the utility wanted, that had to be delivered, means that had to be transmitted, and that has to be taken by the consumers. And if the utility did not have sufficient or surplus generation which can cater the uh, deviations or sudden abrupt load changes, so that wouldn't be, if that is not possible, then the there we faced frequent shutdown and frequent power and power cut, power failures and all these things. So our modern day smart grid aims in maintaining continuity in power supply, and to maintain the continuity, so the load centers, here in the load centers the microgrids have developed, where what are these, means previously it was, nowadays also the load centers are already possessing the PVs, biomass, micro hydropower plant, battery storage, and all these things. So why can't we think of isolating them from the grid itself, if in case any fault occurs on the grid side? So that with that aim, these microgrids have developed. Okay, and these microgrids, we can observe that here micro turbine, micro hydro, biomass generation, PV array. So these are rooftop PVs. So we need to, and also here we have the grid. From the grid side, we also, from the grid side we also have this part. Okay, and this is known as the point of common coupling, PCC. So we already have the grid side, but here we have a breaker. So whenever it's required that the entire power can be catered by, if any kind of fault and all these things happens on the grid side, so it can directly cut this line with the point of common coupling, and after that the entire grid becomes isolated and they can be operated in islanded mode. Okay, so these seems to be quite advantageous, but it also comes with various issues. But for the time being, let's say that, let's talk about the advantages. Okay, but there are disadvantages, not only disadvantages, but the problem becomes more complex to design the protection problem, to design the monitoring equipment, because there's always a not a unidirectional power flow, right? So for that, sometimes from the grid, so we will discuss about some kinds of faults that do occur but can be blindfolded because of the direction of power flow, and the magnitude being dropped, means the magnitude of current or the fault current decreases because of the uh, associated power generating units and means the from the grid distribution side itself. So that minimizes the magnitude of current, which results in minimized uh, actuating quantity, and that they don't let the breaker to trip. So there are some issues or challenges, but still for the time being, let's discuss with some advantages. So you can find out that these advantages, meet the they can meet the electricity peak demand. So they can meet the peak demand. So they have the property that whenever there is a peak demand, we have discussed that the peak demand can leads to the frequency drop, and frequency drop can might lead to uh, what we can say frequency drop can also lead to the uh, under frequency problem, and that can might lead to desynchronization of the uh, synchronous machine. So we'll have to maintain the frequency at the correct value, and for that we always try to have backup or spinning reserves available to meet the sudden peak demands, and these peak demands can be met using the microgrids. Also, they are efficient. So efficient in operation because they need lesser amount of resources, because they are placed in the load center itself, and when they are placed in the load centers, they can directly deliver that generation to the customer end, because but without that too, without any kind of transmission losses. So this becomes a part of efficiency. So customer centric, more customer centric, also customer centric. Okay, then we can also see that they can also be considered as the reliability improved reliability improvement can be observed. So reliability improvement, because there's a continuity in power flow, so there we don't face any kind of uh, outages, blackouts, and all these things. So reliability, it can be maintained. Also, the since mostly they are they are using the renewable modes of power generation. So mostly, because mostly we can see rooftop solars and all these things taking part in the microgrid, so biogas plant. So overall there's a minimization in the carbon dioxide, so that's our aim, and that this becomes means the reduction leads to environment friendly uh, operation. Okay, so now these are basic advantages. So we can also see that here we have a the island microgrid operation can be subdivided into three modes of operation. So grid connected, islanded, and transition to island and reconnection modes, means which can be operated both from grid connected to islanded and back to islanded. So the back to our islanded to grid connected. So these are the modes of operation. So whenever it is required that suddenly there is a failure, a power failure, we can observe a grid side problem or fault that can be observed on the grid side. So instantaneously the grid connected mode of operation can be switched off, and at from the point of common coupling, and then the islanded mode of operation begins. And again, whenever the grid is back to its original operating state, the islanded from the islanded mode of operation, it again reverts back to the grid connected mode of operation. So this is a transition phase which can also be handled in the microgrid architecture. So again, in the islanding part, this is the islanding mode of operation. So here we can clearly see that here we have a distribution substation, right? And here this is the point of common coupling. So this is the bulk supply transmission line. So if we can disconnect from this point itself, then it becomes this entire sky color area becomes a microgrid, which is called the full substation microgrid. Then let's suppose the point of common coupling is not here. Sorry, point of common coupling is here, but the microgrid gets islanded from this point. So let this breaker be switched off. So in that case, we will say it as a full feeder microgrid. So here we can see this is a feeder, this line is a feeder. So from this feeder the loads are being delivered, these are the loads. So this is only restricted to one feeder, so that means this becomes a full feeder microgrid. Now again the cases may arise that from inside the feeder we have to fault occur somewhere here, anywhere in anywhere here in the feeder. Let's suppose the fault occurs here. Okay, so in that case, if the point of common coupling becomes this one and this part is isolated, so that becomes a partial feeder microgrid. This becomes a partial feeder microgrid. Okay, and in cases where from the feeder itself, if a customer isolates itself because he or she or they have the resource of generation, and generation in the form of PV or anything, PV, mostly PV we can consider for practical cases, but a group of customers can also set up biogas units, etc. But for the time being, let's consider the case of PV. If PV, if the customer can sustain from its own PV generation, so in that case, this area becomes a single customer microgrid. So here the customer is only a single customer. So the customer has isolated themselves from the main grid. Okay, so that's the overall view of how these four operation modes on microgrids. We can also have the same operation in the other nodes also, and but the main fundamentals is will remain same. Okay, that the single customer, full customer, partial, etc. So that would remain same. Okay, so I think any doubts where the microgrid's islanding mode of operation. So once the microgrid is islanded, so it has the capability to deliver mostly the loads inside them, and they sometimes we also have the battery storage systems being also present. So the when the microgrid is in operation, so it will have the capability to run its own area, that too without any kind of failure. So the failure or protection or failures is power system failures or power system outages are quite a uh, problematic thing. So that shouldn't be there. So that's the basic aim of developing these microgrids or microgrid architecture. So here we can see that means while islanding, some issues may point at maybe means may show up, means before when these islanding cases occurs, some issues may come in by the means or may be faced by the operating personnel. So like out of phase reclosing, so this is one problem, out of phase reclosing. So this can't be done, right? So whenever the two breakers are in synchronism, then only means the two side, both side, grid side and usable load side frequencies or the line side frequencies matches, then only there is a tolerance also, and when it is within that limit, then only the uh, breakers can be closed, right? So this out of phase reclosing is an issue, is a challenge, and because the circuit breakers will have to be closed, and when it can be closed, it has to be properly in phase. But sometimes these problems do arise that they are to be closed, yet they are not in phase. So some issues related to out of phase reclosing is faced. Then degradation in the power quality. So power quality in degradation is also faced when the voltage or frequency instability occurs. Okay, so suppose when the grid side, if the grid side is on, or grid side is switched on, so in that case, from the grid side we can get the ample amount of power or generation from the grid. But whenever we are isolating the from the grid, so entire amount or entire demand has to be met by the generation or generators placed within that area or within that microgrid. So in case of lower generation, mostly they are governed by the renewables. Okay, so in that case, in the what the distant nodes, some cases of voltage or frequency instability might arise. So now the grid protection interference, so there are protection issues. The protection issues we will be discussing in detail in the upcoming slides. So next, inverter mode control mode switching. So inverter control mode switching. So inverters are, why inverters are required? Because the generation of the mostly in the solar units are in DC. So mostly we have the solar units and they generate in DC. So for that we need to invert them into AC, and when they are inverted to AC side, the loads are mostly AC. Since the loads are mostly AC, so for that these control mode switching becomes tough because they are switches. Okay, so inverter control mode switching is a problem. The malfunction of the protective device. So protective device malfunction, that we will also discuss in this upcoming slides. So I'm not going to detail right now, because protective device malfunction, there can be blindfold operation, there can be uh, operation which was not intended but gets operated because of uh, not the actual program or the relay coordination program being met. Okay, so further these equipments are more prone to damage because they becomes exposed to the utility side. So the protecting uh, or to shield them from various challenges in the distribution side. So since large number of equipments or control equipments, not equipments was also there in the conventional part, but here the control equipments, mostly the control actions were taken from the distribution, from the transmission end. But here isolated control centers needs to be developed, and that would create a major problem. If the damage means, they would be more prone to damage and threats to personal crewmen or safety problems. So that's the issues related to unintended islanding detection. Now, what's the necessity for the islanding detection relays? So the necessity is that here we can see that suppose if there is a microgrid, okay, let's suppose here we have a microgrid, okay, and here we have the main grid from where the we are having the power supply, and from here we have the power supply. Let's say for the time being unidirectional, not bidirectional. Okay, so here we have the point of common coupling, because it's most generally the case is considered here that the microgrid will be self-sufficient to deliver its own loads, but in need they can take the elements, they can take the power from the grid itself. But for the time being, let's not consider the case where they can deliver to the grid, although they have the capability to deliver to the grid itself. So here if we see that in the microgrids we have the DGs placed. So what are DGs? The distributed generation. Distributed generation, DGs. So these DGs or DERs are placed in the distribution side, and also the loads. Loads are also present in the distribution side itself or inside the microgrid itself. So there might be cases where this difference between the load and the DG. So this demand has to be met from grid, because the amount that can't be fed by the DGs, that has to be met by the grid for both the real and reactive. So both the real power and reactive power. But for the time being, if we can see or we can observe that if there is a mismatch, that is this del P amount of power. So considering this del P amount of power, the set point values, these are the set point values for voltage relays with under voltage and over voltage, and these are the over frequency, under frequency for 60 hertz, means for the USSI. So what we need to do is that if suddenly there is a diversion in the direction, not diversion, you can say in the deviation in the direction of the power flow. So for that case, P grid and Q grid, so that would reduce. Okay, so that would cause problem, means reduce in magnitude or direction both. So for that case, there can be either an means there excessive of power or a deficit of power, which has to be made. So for that purpose, though these frequency or voltage deviations might be faced. So for that case, this islanding, whether the system is operating in islanded mode or whether the system is operating in a grid connected mode, that needs to be priorly detected. Priorly detected. Okay. So, and here we can see this is the non detection zone. So if the operation for del P and del Q in the shaded islanding is not detected, means if this difference del P and del Q is within this shaded area, within this shaded area, so in that case the system won't island. But if suppose there's a major difference between the grid side and microgrid side, which might be an inference can be drawn that a fault has occurred and sudden power flow started, sudden current flow increased. So for that case, this overflow, overcurrent relay, over voltage relay, voltage not the cause of voltage here, but set points values are already present. So both these over voltage, under voltage relays would trip. Okay, so that's the cause of islanding. And there for the non-detection zone, there are the presence of these real and reactive power mismatches that leads to the detection. Means based on these mismatches, that leads to the detection. So okay, so, okay. So now we have various standards like the standards 1547 IEEE standard is there for this islanding detection, and based on this standard, systems or equipments needs to be detected or designed. So these are the islanding detection techniques. So that can be passive, active, hybrid, or communication based. So these are the islanding detection techniques, right? So these are the types of islanding detection techniques where in the passive, so in the passive islanding detection technique, we will have to continuously monitor the, okay, so passive islanding detection techniques, we can have to continuously monitor the quantities like voltage, frequency, impedance, phase angle, sequence components, etc. So based on that, we can find out that how and why these are, means we'll have to first we'll have to find out why we are detecting. So once we find out that we are detecting because this islanding detection needs to be done because of these criteria some that we have discussed. So for that we'll have to monitor the power quality, impedance, rate of change of frequency, then rate of change of voltage and phase angle, and some signal processing based devices. So again, coming to the active islanding detection techniques, so we'll have to inject some signals. We'll have to inject signals, okay, through inverter controllers, right, rather. Okay, so in case we have the positive feedback, in that case, here we also can use the positive feedback to find out. Okay, so some active part, and hybrid is a combination of both active and passive. Hybrid means both active and passive islanding detection techniques would be followed inside this single form, and communication based is based on PLC, SCADA, SCADA system communication, where we can monitor the breaker status. Okay, so okay, so we can also find out some techniques related to the power quality monitoring. Okay, so in the power quality monitoring, first based on the power quality monitoring, whether when the detection would be given, the detection that there is a islanding mode of operation or non-island means grid connected mode of operation. So for that we have some stages where the single it is measured single. We can also see there in the um, single phase operation, single phase RMS voltage at PCC. So first it is measured, and then a mean block is used. Mean is taken. Mean block is taken, and then we can obtain the VRMS mean. Okay, and using that VRMS mean, we take the derivative. The derivative of that is dVRMS by dt, and using that we have, after finding the derivative, we again find the mean. Okay, so after finding the mean we find the RMS value. So RMS value, frequency RMS, and after that we again find the mean, so that leads to FRMS mean. And whenever this value is greater than or lesser than threshold, that indicates the islanding. So whether the system is islanded or not. So if it is greater, then island is detected, or lesser, island is detected, not detected. So this is power quality monitoring based technique. So after the final, after the all the stages, when based on the final graph, so we can observe that at a point of time, some values, all the after approximating all these values, the final value would be like a switching system. Means this can't be a direct switching like this, so that can be in the form. So if it is showing in this form, and after that there is a rise in the value like this, so that crosses the threshold, and that acts as a detection technique. So again, from the impedance based monitoring we have the other technique, impedance based monitoring technique. So here, let's suppose we have the capacitors, inductors, and all the resistances all being placed. This is for the grid side. Okay. And on the other side, we have this is the grid side, this is the microgrid side, but not in the microgrid form. It is operating in the grid connected framework itself. Now, if suppose here the point of common coupling, if there is a breaker, okay. So if any fault occurs here, so in that case, the the microgrid would be isolated, and this grid portion would be eliminated. Okay. So when the grid portion is eliminated, that itself implies that the grid has islanded itself. Now the microgrid has to, now in the previous case, if the impedance, the impedance would be governed by both the grid side impedance as well as the, if we consider name them as microgrid, so grid side and microgrid side, both the impedance, but pre this that consider Z pre, but Z post that would only be governed by microgrid side impedance. So there would be a change in total impedance. Change in impedance. So based on the change in impedances, we can detect that microgrid is in operation. Means it is operating in islanded mode of operation, or is it operating in a grid connected mode of operation. Now again we have a technique where with the rate of change of frequency, with the rate of change of frequency, we can detect whether the microgrid is islanded or in the grid connected mode of operation. So if we can find out that the change in frequency, like the omega, from the omega rad per second, if we can find out this ddt of, would give hertz per second. Okay, so that would result in the 1 by TAS plus 1. So that is the measured window. So whatever we would get after that, hertz per second, so we can detect that if it is within that threshold or not, then that is uh, frequency rate, based on that rate of change of frequency. So that monitoring is that is based on rate of change of frequency, that is based on DFDT. So if that DFDT value is greater than some limit, then it is a change of frequency is observed, and that can be considered as the what I could say, what I can say is that that can be observed as a change in frequency, would be resulting in the identification whether it is grid connected mode of operation or islanded mode of operation. So, but the change of frequency has some drawbacks. So the drawback of, so the drawback, firstly, there has to be a minimum power mismatch of 15%. 15% power mismatch is required. So 15% has to be there, and also based on the loading and loads and generators dictate the operation. Okay, so there these are the issues. And okay, there is another also operation ROCPA, rate of change of phase angle. So in the rate of change of phase angle, we can observe that del of divided by del t, rate of change of phase angle, and rate of change of frequency we have already discussed, del f del t. So overall, based on these islanding detection techniques, the entire power protection or grid protection system is delivered. Microgrid protection is delivered. Now, if in this case ROCPAD, that is the rate of change of phase angle deviation. Okay, PAD we can also say rate of change of phase angle deviation. So it can be observed that the energy of rock pad, that of voltage, of the voltage of these at the point of common coupling, means voltage at the point of common coupling, that is not zero. So this can be observed that the energy at the point of common coupling after islanding, energy is non-zero, and also the non-islanding disturbances, the energy signal of this rock pad is non-zero for up to few samples. Okay, so and later on it decreases to zero, but till then it has some energy whenever this action takes place. Okay, so that's the first part of islanding detection. So here we can, so till then if you have any doubt you can ask. Wait for 2 minutes and then we can start the island detection for the microgrid, where rate of change of negative sequence impedance. So this is the technique based on negative superimposed impedance or superimposed negative impedance, negative sequence impedance. So this technique is far more, we can be much more uh, emphasize on this technique because we can rely on this technique more than the other parts. So any problem or any doubt you can ask. Then we will discuss. So the basic understanding why the need of protection or islanding detection is required, that should be cleared by now. That what's the need? The techniques we can also refer to the slides of the lectures itself. Okay, so here we can see this is ROCO SNSI. This is the rate of change of superimposed negative impedance. So here we have impedance which is the post and post islanding negative sequence impedance, and pre is the negative sequence impedance in the grid connected mode of operation. So pre and post negative sequence impedances needs to be found out, and for that we need to have the information of the negative sequence voltages and currents. Okay, so after we have the information of negative sequence voltages and currents, then we can store these pre and post events, pre and post uh, voltages or currents. Okay, and the sampling frequency that is being followed is taken as 1 kilohertz, and then we apply the phasor estimation techniques. This is the algorithm that is being followed for perform the negative rate of change of negative sequence of superimpose negative sequence impedance. So phasor estimation is performed using WLS, and once the negative sequence impedance is found out using these phasor estimation techniques, WLS techniques, then find out we can find out the Z pre or Z2 pre, we can say, because this is the negative sequence, and Z2 post. And after using these two, since we have the values of voltages and currents, we can find out the impedances, and using the values of impedances at the tth instant and the t minus 1th t plus 1th instant. So if this is the point of time t, and here it is t, if we are at t and it is t plus 1, if we can say. So this change we'll have to detect, that is the t plus 1 and t minus it means t. So based on that we can find out this rate of change of negative sequence impedances, and as we can see that normal operating cases we will be observing them to have or to possess values to be more nearing towards zero, but as we move towards the uh, if some action means some islanding occurs, in those cases these values would change. Okay, and that helps in the detection of this, whether the system is operating in islanded mode or whether the system is operating in grid connected mode. Okay, so there are tests which are performed in uh, IEEE systems, and this was mostly uh, performed in this microgrid architecture in considering IEEE 13 node test system. So the mainly the we can also have some discussion on this hybrid islanding detection, where the passive and active both islanding detection techniques needs to be followed. So active as well as passive. So in the passive part, at zero power mismatch, it is difficult to detect why the need is why this hybrid is required. So during the zero power mismatch condition, it's difficult to detect the islanding condition, and since the electric quantities or variation is very less. Okay, now for the other part, the active, only active cannot work. Why? Because either they drive the islanded system into unstable mode or degrade the power quality. So to suffice this to negative impacts, so we'll have to have some hybrid islanding mode. So here the system will be using monitored using passive island detection techniques, and the island is predicted and further checked by active IDE. So a bilayer protection or bilayer actuation takes place to detect whether any island ding has been formed or not. So significant reduction in power quality issues, and reduction in the power quality issues, and also detection capability is better than the passive. So the active this hybrid becomes much more beneficial when compared to the active, only and passive only islanding detection techniques based on these criteria. So, so that is mostly of the islanding detection part. So also we have signal based. Okay, so signal based signal based operation as well as a signal injection, not signal based only to say, and positive feedback based. Positive feedback based. So in the signal based mode of operation, disturbance signals are being injected. Okay, so mainly we inject disturbance signal. These are mostly informative sessions because the things are, until and unless they are done in practical and in this discussion session, if you have any doubts we can discuss, but in these practical session, in these uh, online sessions, we can discuss to the extent how these things are actuated and how are these frequencies, means these frequency signals can be both low as well as they can be high. So also they can be negative sequence or they can be pulse signals. Okay, so these signals are injected and the islanding detection is based on this the electrical parameters. So behavior of these parameters at the point of common coupling is measured and estimated. So based on these disturbances, so based on these disturbances, uh, the at the point of common coupling, the detection, means these islanding detection or active, these are active island detection techniques they follow. Okay, now from the positive feedback point of view, we can have the information like the frequency, like we can say phase angle, voltage, etc. So based on these deviations, they access these information, they access feedback, and based on this feedback, it can be detected whether the system is in whether the system is operating in uh, islanded mode of operation or grid connected mode of operation. Okay, so various signal injection techniques are followed where the harmonic based, let's if we can say that uh, before islanding and after islanding some harmonics gets injected, and these harmonics, since they are high, they can be high frequency signals or low frequency signals. For initial condition they superimpose, but whenever they can be superimposed, but during this islanded mode of operation at the point of common coupling, they tend to have a different behavior, and those different behavior leads to the detection that whether the system is in grid connected mode of operation or islanded mode of operation. Okay, also they we have this ADVV, we have already seen in the lecture itself. ADVV 1 by T upon, means here we need to calculate the mean value, and for that it is TT, ADVV, okay, and T minus T and T. Okay, so here it is mean value. So mean absolute d-axis voltage. So mean absolute d-axis voltage. So we'll have to calculate the mean value, and also we can also have the mean absolute rate of change of d-axis voltage, which is also signified as rate of d-axis voltage, ARO, not dVV, sorry, ARO, uh, CODV, rate of change of d-axis voltage, rate of change of d-axis voltage, and the mean value can be implied as d of Vd t dt. Okay, so at the point of time, so based on the mean value, we can be calculated based on Vdt, and for the mean value, we need to calculate ARO CODV mean, and this mean value would imply the change. Mean value would imply the change. Okay, so that is ARO CODV, ARO CODV, and it is dt, and t minus t to t. Okay. So based on these two detection techniques, the signal generation based detection techniques or active detection techniques, these two can be altogether implemented and to have a better trip signal, because when we rely on multiple parameters or multiple factors to detect a single trip signal and to find out whether the system is in islanded mode or grid connected mode, and all these things becomes much more beneficial, because we are relying not only on the single value but on multiple values or multiple uh, not values, we can say multiple decision making quantities. Okay, so that's the thing. So next we can discuss about the fault fault part. So if you have any queries, you can ask. We can. This is the microgrid protection part. Microgrid protection part. So since we have discussed why the microgrid is required and how the microgrid benefits our modern power system, uh, modern power system devices or modern power system ways, that the development of equipments and development of continuity in the already the power supply was there, but it was conventional, and the continuity was not there. Means there were frequent disruptions in the power flows, and for that the power flows in the distribution side were mostly facing those issues. Like in the present trend or present day scenario, where we have these kind of options where we can set up the microgrids. And what are microgrids? These are, as I have previously discussed, that these are self-sustained grids, and they are placed in the load centers itself. So that gives an immense advantage, that we can minimize the transmission cost, we can reduce the transmission cost, and on top of that, we have the feature that they can be controlled as per the ways or as per the microgrid operators or as per the customers, because mostly the customers are present in these microgrids, that they have a very different viewpoint. Means what the utilities want, they want their generation, means they previously wanted, but now they are bound to operate on a very different or wider scale because of various reasons, like we'll have to fulfill or we'll have to maintain the power system continuity, because that's the aim. So one grid, one nation, one frequency. With that, some protection issues, but challenges do arise in case of microgrid. So initially we have discussed some advantages, but now problem that we face in the microgrid in the view of microgrid protection, that is uh, first first is these protections should protect or protective equipment should isolate the very small utility portion also, because they should be capable of islanding each and every area, so the system becomes more complex first of all, because as we have the DGs from placed on the rooftops and everywhere, means on the distribution side we have a large number of DGs being placed. So with these large number of DGs, they means they deliver data directly, means unidirectional, which was previously unidirectional, but now it has become bidirectional. Now with this bidirectional operation, the major issue lies in the detection, means major issue which we face is that there is a continuous change in the direction of power supply. There is a continuous change. Okay. And this continuous change we can observe in the as a part of the dynamic levels of the fault current, as a bidirectional fault current, as a fault stripping and blinding protection. So first of all, let's discuss what is the dynamics in the level of fault current. Okay. Now, since let's suppose here it's the microgrid, okay, and here it's the point of common coupling, and here we have DGs connected, etc. Loads are there, everything is in place. So, previous, let's if we say or if we compare them with the previous operating scenarios, here these DGs were not placed. Okay, DGs were absent. So since the DGs were absent, what we had is that the power flow direction was only this direction was. Now with this power flow direction, there were no breakers required, nothing required. But and if the system would have been easier if the area or the grid that we can see, it would have a single DG placed at one end. So if suppose here's the generation, here's the grid, here the PCC, and here we have another DG or DER in the distribution or microgrid side, and it is also delivering. And suppose a fault occurs, this part will be there are some buses from where loads are connected, etc. Both DERs and DGs used to feed, but now the problem has, if there is a fault, then only one, this is one direction or this is another direction, two direction is there. But in this case, where multiple DGs are placed in the diagram that I've shown, here multiple DGs are placed here and there. So the direction of fault current becomes unanimously hard to detect, and the magnitude, because this line, if suppose this DG was previously feeding, this line would have carried let's suppose to 1.2 per unit of current previously, but now with this DG in place and this DG also feeding this way, this current or this reduction, let's suppose it is now reduced to 9.98. Now what can be the set point value, of this what can be the set point value of these uh, protection equipments or protective equipments, because there's nothing to be found, means nothing to be relied, because once this line value becomes 1.2, and again at another point of time this point value becomes 9.98, so what would be the set point value? So that is the issue, which is this case of dynamics in the fault currents. This is the dynamics in the fault current. Now let's come to the case of bidirectional fault current. So previously, mainly our systems are protected using both the overcurrent units as well as the directional units. Now with the overcurrent units in place and the directional units in place, our main aim is to minimize the power outages. So with both these units were previously placed and now also they need to be placed, but that would also incur cost. So how and where they should be placed, what conditions should be previously monitored to enhance the power system continuity or power flow continuity in this microgrid, that should be taken care of. So if suppose this unit is only single or unidirectional, let's suppose this is the unidirectional unit. Sorry, not direct, non-directional unit, only overcurrent unit. So if there is a fault on this point, so that fault would be fed by this grid, that fault would be fed by this upper part of the feeder. So there is a very good chance that this breaker would also trip. This breaker would also trip, but that is not required at this point of time, because since without directional unit, this would trip due to trip due to the absence of the directional unit, that this unit would trip, but that is not again required, because this trip is not accepted at all. So if we had a directional unit being placed here, then that would resulted in an isolation from this end, and this breaker wouldn't have been tripped, and they can be, and if this part that this breaker is tripped, then this portion or this feeder is being out of operation, and the point of from the point of compound coupling, the grid can also feed this part, also this part, etc. So the direction, the bidirectional fault current flow, this is a major problem, and this thing needs to be taken care of. Okay, directional fault current, bidirectional fault current, because the fault current which was previously flowing that way, now it can flow this way also, as shown. Means previously it was only this way, now it can be, because distribution side was only unidirectional. So that is a major problem. Now come to the case of false stripping. What is false stripping? So we can observe that suppose this case can be overcurrent relay. So this case is the as we have discussed that the feeder one. This feeder was in healthy, was a healthy feeder, but this feeder got tripped just because of this distribution side. Sorry, because of this fault occurring on this point at this point. Okay, so this healthy feeder got tripped because it was because due to the absence of directional unit. So that leads to a false tripping, because that line was not intended to be faulty. That line should not have been tripped. Okay. And another one is blinding protection. So blinding protection means, let's suppose here in the point of common coupling, we are having a power flow of, let's suppose 1 point, let's consider this 1.5. It is, let's suppose 1.5, but in the presence of in the presence of uh, DGs here and there, this fault current, now this breaker has to be set at a particular value, right? This breaker has to be set at a particular value. Now with this breaker being set at a particular value, there has to be some problem. Okay, so that's the case where point of common coupling, the magnitude reduction. So with this magnitude reduction, initially previously it would have been considered as a fault if there would have been a fault, because now we have the synchronous based DERs, but now with the reduction, magnitude reduction, now it will be treated as a normal case. Although normal case, although we have a fault, but the fault current is made by a fault current magnitude reduces. Okay, so these are major problems or major issues that we face. So, uh, so these are the protection issues that we face. Okay, now we have dynamics in the level of fault that we have discussed. Here, these are the pictures that we can see. Dynamics in the level. So previously only main grid was only fitting, that is IGR grid, but now due to the GGs in place, so G1 would also participate and G2 would also participate. So there is an increase in the total fault current, total magnitude of fault current. Okay, that we have already discussed. Now the we have already discussed it here that uh, now this is the case of bidirectional. Yes, so bidirectional portion is, suppose we have a fault here. Okay, so with the fault occurring at this point, the this DG is delivering power this side, this DG is delivering power this side. So the fault current is operating from the bidirectional side. Again, this is the false stripping. So as I have discussed that if the magnitude of faced by CB1 magnitude is not the CB1, rather to say the relay for CB1 would face a lesser fault current. Okay, just wait 1 minute. Ah, so this is the case for relay would sense a fault current which is at a much lower level. So traditional relays or unidirectional overcurrent relays would operate it here. Would be unable to operate. So we need to design a better relay coordination program, right? And also we have the blinding protection. So here it would have been fault. So here current would be flowing and R1 can trip, and it is unintended. That is not at all required from its side. Okay, so overall this is the, so when fault contribution in this from this G1 exceeds this current setting, means the fault contribution, this current flowing from this side to this side, if this value exceeds, so if the relay setting exceeds the relay setting for R1, so that would result in a tripping of this relay. Okay, so power interruption unnecessary will be facing here. So this is the case for false tripping. Okay, also the blinding protection here, the this is the utility side grid, the CB. So this C circuit breaker will face a relatively relatively low value of current, or rather to say fault current. Okay, so with this, the majorly the resultant would be a blinding action to this circuit breaker where the breaker won't be tripping. Okay, now here it is a synchronous based DER. Here it is the inverter based DER. So what we can observe is that there are two kinds of fault levels for the synchronous DERs uh, and the IBR means IBDERs, inverter based DERs. So in these two DERs here it is 5 times and here it is 2 times. So what we can observe that the resultant, this is the summary point. Means here we can see all these operations that we have discussed. So for R3, if a fault occurs here, we can if this trips, then that would lead to a false tripping. Again, if the uh, grid is this is blinded. If grid is delivering power and not delivering the amount of power which is required once it a fault has occurred but the power values and the fault current values gets reduced and this grid doesn't trip, so that would result in blinding, so false tripping, blinding. Okay, so overall what we can observe is that we will have to detect or deliver some better fault current determining techniques for the microgrids so that a better control strategy would be developed that would deliver the best possible operation without hampering the power flow. Okay, so that's the major aim, that's the main aim. And in our case also, in this case where the overcurrent relay, directional relay, so these only overcurrent relay cannot save the entire power system or entire microgrid from tripping. And what are these overcurrent relays? These would operate based on the magnitude crossing. Means if the threshold of this magnitude crosses, then the relay would trip. Relay would send the trip signal to the breaker and it would trip. And we can also have see various kinds of relays. So IDMT relays where with the time, sorry, we can consider this as a time and we can consider this as the magnitude of fault current, that with the increase in the magnitude of fault current the time of operation minimizes, so that is inverse definite minimum time lag. So here we can see a schematic diagram of the microgrid with control center, and here we can see that this is a microgrid control center. So this comes as an evolution of the normal uh, control center or distribution control centers that we have previously discussed, that we had distribution control centers at the apex, sorry, the transmission control centers at the apex, the NLDCs, I think you all are aware of these things since we have discussed previously that initially we have NLDC pertaining to the Indian context, then we have RLDC, then we have SLDC, then we have ALDC. We can also say sub LDC. So NLDC is governed by POSOCO power grid as a part of power grid. Yes. POSOCO runs this NLDC. RLDC also a part of POSOCO itself, but we can say there are five RLDCs. Yes. Then we have SLDCs. Mostly they take part of the states. The bidirectional occurs between the area load dispatch centers are also governed by the state discoms. So the main problem here is that the information was previously, if we consider the previous cases, the information is being delivered by the NLDC itself to the lower levels. But now with the uh, other apex bodies or other uh, development of with the development of smart distribution grids, because our main aim is to minimize the cost, and one of the major costs lies in transmission, and other part is that transmission expansion cost is quite high. So what we need to do is to minimize our cost. So here what we can say is that with the with the distribution side, they are trying to develop near the load centers. So distribution side, uh, we can say DES enhances in the development of power in the near the load centers. And when we can develop or generate the power in the load centers, that power can be catered in the distribution side itself. Okay, so there's a mass reduction in the entire power flow, mass reduction in the transmission system cost, because For the entire system or new generating units to be developed at other locations, transmission system, the major constraint, transmission system expansion. Although the expansion work is going on, but that is quite a problematic part. Okay, so transmission system expansion acts as a major challenge. So we can reduce this thing, okay, by developing these generating units at the load centers itself. So, but the monitoring part, which was previously done from the TSO part, TSO, now led to the evolution of DSOs. Okay, and with now to also help or aid in the DSO objective, meet the DSO's objective, it can as a part of sub part of DSO, we can say microgrid SOs. Once microgrid control centers are getting established inside the microgrids to enable continuity. Okay, so with this we need to have a microgrid control center. So here we have a microgrid control center where the control center has proper communication lines to transfer data to and from to the relays, and based on this relay circuit breaker would operate. So relays, for the time being, let's consider them as relays. So because the information has to be sent to the relay. So the microgrid control center, they have the access to the entire relays, all these relays, and as well as from the point of common coupling PCC, that is the grid side, because the mode of operation to change or to transfer to the other mode of operation, the PCCs, at the PCCs, the information of whether the system is operating in islanding mode or grid connected mode, that needs to be properly governed. Okay, now this overcurrent relay. So with the overcurrent relay, we can say that voltage in these areas, in these relays, we can say in the microgrids, voltage can be considered as a polarized quantity, and current as the actuating quantity. Since since the phase angle of the voltage, however long the voltage means, the microgrids are not large in length, right, or large in area. So there has to be some limitation in the line lengths. So with those limitations of line length, what we can observe is that the voltage drop or phase angle change for the voltages uh, doesn't seem to be much prominent. So for that, what is done, the current is taken as the actuating quantity with respect to voltage, where the proper phase angle deviation can be observed. So here we can see There's a phase angle change here and here. So current acts as an actuating quantity, and based on that, this relay coordination program is developed. Another important part that we will be discussing on the upcoming days, because this course, I think on the next week, this course, this section would open for the viewers. So adaptive relaying. So since we have discussed about various challenges like the fault correction in the directional unit, sorry, the overcurrent unit failure, fault current increasing, etc., etc. We have discussed various things. So what's our discussion is based on? The discussion is based on adaptive relaying. If we can, based on challenges which we face if we use the traditional unit, but with uh, so much diversity in the generation, will it be systematically possible to impose directly the change in various changes to, because the relay has to be designed before the relay is implemented, it has to be designed considering all those test cases. So is it possible on a direct approach? Is it possible? There are very much limitations, because means before applying, all the cases needs to be uh, taken care of. But is it possible for each and every customer, or each and every, or the distributor, or the microgrid utility or distribution utilities to consider all those cases and develop a relay which would be having all those uh, contingent situations for which it can operate, because the load changes and everything for each and every residential areas, the load changes are becoming different day and day, each and every day it's becoming different. So, and how can we develop a relay which can have, or how fast we can update the relays? So it, everything becomes a great challenge, that how fast we can update the control strategies, because these are also tough. The control strategy designing is also very much tough. So for that, we can, what we can do is that we can develop adaptive relaying schemes. So adaptive relaying schemes, the advantages of adaptive relaying schemes is that they have the, suppose we have a long line. So in this adaptive relaying scheme, whenever we are delivering a data in the uh, suppose there's a change. Let's suppose some loads are there. We have a bus. We have two, three loads here. Okay. In similar cases, we have loads here. Okay. Dot. So the problem is that here we have multiple operating scenarios. So, and suppose relays are here, here, here. So we have a huge diversity of operations that can be possible. So one thing we can do is that we can deliver adaptive relaying. So in this adaptive relaying, what we can do is that we can develop the relay actuating quantities based on load increments, We can also use, probably we can also use data present operational data which can lead to updating. So the may mostly we'll have to play with the thresholds, because it is the threshold which can or which will deliver action. Based on this threshold it will deliver the action, right? So it is the threshold based on which the deliver that dedicated action is delivered. So we need to update those thresholds, and that updating of the thresholds can be done probably with the help of various data driven approaches where the data gets transferred based on uh, data gets transferred to the utility centers, and the control logics can be implemented and revised automatically, and the relay can send trip command accordingly to situation. So these things can be done on a greater scale, but they we need to differ the threshold values, and based on those threshold values the relay would be sensing some additional part, and relay would send trip signal and update them again with say another problem is that in the programming we need to also take care of these protection schemes which are based on two layers. Means suppose we have a grid here, suppose here, and we have another relay placed here which is actuating a circuit breaker. So in this case, so relay, when I say the word relay, it implies both the relays as well as the breaker. Means the operation would be done by the breakers, right? So let's suppose a fault occurs in this area. So initial case, this breaker would take care of this fault. But problem is that if suppose this breaker somehow or the other maloperates, that maloperates means if it doesn't operate. Let's consider the case it doesn't operate. So problem would be there that the fault would propagate, and the fault would increase. Means the fault current, there is a loss of energy, loss of resource, everything. So why to do that? So for that we also have a backup protection scheme. Now this area which was firstly a part of that area, a specific time is allotted, right? A specific time is allotted for this relay to actuate for that fault. Now if this relay doesn't actuate to this fault, after a stipulated amount of time that it has been assigned, then these backup protection schemes also render the protection to that point itself, to the fault. But for that relay to operate, this amount of time, the time in which this relay operates, plus circuit breaker operating time to the power of x, means where the x is the amount of uh, time, or we can also say that coefficient of time that is allotted for the breaker, for the relay, for this relay to operate, or the breaker to operate based on the circuit breaker time, and an emphasis also given to that breaker time, and the weightage, how much weightage is based on this factor k. And after this operation, this entire time elapses, then only these uh, backup, this relay acts as a backup for that area. Now, inadvertently, we cannot deliver or demonstrate any one of the relays to act as the backup. So there are limitations that which relay would act as a backup of whom. So the entire relay coordination program itself leads to a much larger and diverse area of research. So these are with the renewable integrations in place, these relay coordination program and all these things, they are becoming much more complex and much more uh, tough to design them, because due to the bidirectional power flow, the conditional monitoring of these equipments, the load assessment needs to be done properly, and if everything is working fine, then only this entire operation can be acting smoothly, because these are the microgrids are the present day grids that do take part in a much larger scale for the power system uh, continuity of the to maintain the continuity of the power system. But somehow or the other, we do have to take care of uh, system uh, fault, the system fault, and all these things needs to be properly monitored. And for that part, adaptive relaying do play a very important part. So some PSM, TSM can also be uh, developed, also can be adjusted, the flux setting multiplier and time setting multiplier, and accordingly the results can be obtained. So this is the maximum positive sequence default current, maximum positive and fault current seen by each relay, the lowest uh, time delay setting, the coordination time interval, positive sequence component fault, positive sequence fault current seen by the backup relay, the time delay for the backup relay. So it's not a single operating scenario, it's a multiple stages that operate all together to deliver backup protection scheme. Okay, so that with this we come to the end of their discussion part. We'll discuss some question and answers, and then we will end up today's session. Uh, so I think it's visible. So microgrid has an 800 kilowatt load and 200 kilowatt solar generation capacity. Find the power imbalance when the islanding condition is present. So we need to find out del P, since it's conditioning only to real powers. Okay. So previously we have discussed that the del P is the in the microgrid is to be catered by load and the DG. So that would be delivered by the grid. So here 800 is the load, DG is delivering 200 kilowatt. So the remaining 600 kilowatt has to be delivered by the grid. The rate of change of frequency islanding detection, rate of change of frequency Rokoff identity performance scheme is affected by type of load, generation, generator inertia constant, both none. So rate of change of frequency is dependent upon. You can definitely go through these videos because that will be uploaded in YouTube. So when there is a load imbalance, load generation imbalance, then only we face the frequency problem and also generation inertia constant. So this change in frequency, this change in frequency gets scattered by initially by the generator inertia based on not only generator inertia but the generator rotor energy stored. Okay, so that generator energy that is stored, that acts that kinetic energy, that kinetic energy of the generator rotor, which is the acts as the inertia, which is based upon the generator inertia constant, that also acts as a promising part for the rate of change of frequency. So the answer would be both B and A, or A and B, you can say. The ROCTA energy signal is non-zero for few samples during non-islanding distance rock pad we have discussed, which is non-zero xt for 2 or 3 samples. Later the energy signal reaches to, after 2 or 3 samples it reaches to 0. Okay, so okay, let's discuss more questions. From the previous days also we can discuss some questions like the storage part. I have some questions related to storage. So this kind of fault questions, next day also we'll discuss faults and then we can discuss but some flywheel related questions, some storage devices related questions we can discuss. These are taken from the previous year question papers itself. So here it would be 1883. Okay. Number two, megawatts. Tehri pump storage. 1000 megawatts, right? Here is the question: energy storage tender activity increased by dash percentage in 2021. So B it is 45%, C it is 41%, D it is 54%. Two, three questions more and then so it is 41%. Which one of these is not an active cell balancing method? Not. Emphasize on not. So out of these, overcharge is not an active cell balancing technique. Okay. And this question. These questions I'm doing because these type of questions can come in the questions so final exam. So you can go through them. So why BMS is required? So first, it increases the battery pack efficiency, optimal usage of the energy inside the battery, reduces the risk of prematurity of the battery, and all of this. So here as the point suggests, so since it increases the battery optimal also usage, reduces the risk, battery pack efficiency increases, so optimal usage, so risk of prematurity of the battery. So all of these the correct option. So with this we come to the end of today's session. And if you have any questions, you can ask today, next day, anywhere. I'll upload all these things on the link as well as the slides also. Okay, thank you for attending.